It's my pleasure to welcome everybody for the research talk for the session, and our speaker is Alexandre Krajenbrink from CISA and INFN in Trieste. He's going to talk about Fredholm determinants, Painlevé equations, and the Zakharov Shabat system. Welcome.
Thanks a lot, Leonid. Thanks for this introduction. And today I'd like to talk about some topics that spark the interest of most of you. And exactly as Gregory, I'm a physicist. So I'll try to give you a little bit of a physicist perspective on all of these problems. And before entering into these algebraic curiosities, which relate Fredholm determinants, Painlevé equations, and also the Zakharov Shabat system, I'll try to give you a little bit of an introduction of how I came to this problem. And this will serve actually as a transition from the course of Gregory. So originally, I'm not coming from a many-body physics background as Gregory, but rather from the Kpz background. So originally, I was studying the Kpz, and for those of you who are not entirely familiar with the problem, let me just remind you quickly what this is about. So originally, the Kpz problem was about growth of interfaces. So imagine that in front of you, you just have a piece of paper, and on one of the edge of that paper, you're putting some bacteria. And if you're putting the bacteria evenly along the edge of the paper, and then you let them evolve and grow on that paper, you would expect that the bacteria are gonna grow, and the growth can be described by the front of an interface. And if the physics was completely perfect, if all of the bacteria were exactly behaving in the same way, if you didn't have any different in the thickness in the paper whatsoever, you would expect that the growth of the interface would be purely linear, like you would have in this animation. But in practice, life is not that perfect, and you have some stochasticity in biological processes. You might not have the same chemical composition everywhere in the paper, so you would expect indeed that the growth of the interface would be kind of rough. So the front of that interface would be described more or less on average by straight line, and you would have fluctuations on top of that line. And in terms of that growth has been described in the 80s by Kardar-Parisi-Zhang, and actually wrote down a stochastic nonlinear differential equation to actually the interface. So their equation describes a height field h, depending on the space variable x and time variable t, and the equation is as follows. So the equation is at the beginning kind of a heat equation where you would add two extra contributions. The first one is a nonlinear contribution with the gradient, the square of the gradient of the height. And the second contribution is a white noise, actually accounting for the stochasticity and the external noise in the model. And when talking about the growth of an interface, something that is crucial for a physicist is actually talking about geometries. So when you want to study the growth of a problem, you should start from some initial conditions, some initial geometry. And for the Kpz problem, generally, there are two types of geometries that you can consider. You can either consider a geometry in the full space or a geometry in the half space where you would have some kind of a wall or a boundary. And in general, for everyone here, there are three geometries that people always study in the full space, which are the flat initial condition. So you would start with really an interface which is completely flat, like in my example with the bacteria in the piece of paper. The second geometry of interest is in general the Brownian initial condition, where you would pin the interface at the origin somewhere, and you would have two Brownian motions running to the left and to the right of this origin. The Brownian motions are independent, and you also give them some wedge, some drift W, which is represented on the right of that slide. And the third initial condition generally of interest is the so-called Droplet initial condition, where you would take, for instance, the drift of your Brownian motion to go to plus infinity. So you would really expect some kind of really steep triangular initial condition. And since this equation was derived by Kardar-Parisi-Zhang, a lot of people that are actually in this audience today put a lot of efforts in trying to get information and exact solutions to that equation. And in particular for the full space problem, the Droplet initial condition was solved by many people in around 2010, the flat initial condition in 2011, and the Brownian initial condition around 2012 and 2014. But because the equation is inherently stochastic and nonlinear, I actually have to tell you what does it mean to solve this kind of equation. And that will be the first transition with the talk of Greg. So it turns out that for the Kpz equation, if you're looking at the interface at a special point, like for instance, the height at the origin, after a given time, it turns out that there's a remarkable result, being that a certain generating function of the Kpz height is actually equal to a Fredholm determinant. And this is exactly what Greg was saying a few minutes ago. And in the case of the droplet initial condition, this generating function is equal to a Fredholm determinant, which I will call an inhomogeneous Fredholm determinant, which has actually two properties inside. So there's a kernel, which is the airy kernel, generally appearing in random matrix theory, and a certain measure, a certain additional factor, which is the so-called Fermi factor, which is exactly the one Greg was mentioning in his talk. And in the problem of the Kpz growth, generally you don't have a finite temperature, but what you have is actually a finite time, because the time governs the dynamic of the whole thing. And there's a mapping being that the time of the dynamics is actually the inverse of the temperature. So if you're looking at the process at a finite time, it's strictly equivalent as looking at the process as a finite temperature for fermions. And if you're looking at the convergence of the process at infinite time, then it would amount to study fermions at 0 temperature. So this is actually at the core of this conference about finite temperature combinatorics. And another remarkable property that you can have from this is that now if you look at the infinite time limits of this generating function for the Kpz height, then you will find that the probability of observing the Kpz height at the origin after a given time, after a long time, is actually given by the Fredholm determinant describing a Tracy-Williams distribution for beta equal to 2. And in the case of the Kpz interface, what you're actually looking at is the probability that the Kpz height has a linear growth. So there's an average velocity, which would be -1/12 here. And the fluctuation around this linear growth would be of the order t to the 1/3. And this exponent 1/3 is really characteristic of the Kpz universality class, rather than the Gaussian class, for instance. So already for all of you that know integrable problems, the fact that you have Fredholm determinants appearing here should actually ring a bell that there's a strong connection with integrability. And another really specific and remarkable property that Greg did not mention in his talk is that there are further connections with even Painlevé equation. So indeed, if you're looking at the Fredholm determinant appearing at infinite time, so just the Fredholm determinant of the airy kernel, if you take its logarithm and you differentiate this twice, then this object will be related to the famous solution of the Painlevé II equation. And this relation was actually found by Tracy and Whedon a few decades ago. And the remarkable thing is that this identity, this mapping actually extends at finite time or finite temperature. And this was first proved by Amir, Corwin, and Castell in 2010 when they derived the solution of the Kpz equation. And in this case, if you're looking at this finite temperature Fredholm determinant, once again you take its logarithm and you differentiate it, then you find that this is related to a weighted L2 norm of a function Qt of S, which is not the solution of the Painlevé II, but which is the solution of an integro-differential Painlevé II equation, or we can also interpret it as a finite temperature Painlevé II equation, which comprises actually the derivative of the Fermi factor sigma prime. And to find back actually the infinite time limit, you would solely consider that sigma prime is a delta function, and from this you would find back the regular Painlevé II equation. And even though this equation was derived in 2010, there has been much interest recently around this, and people, especially Castell and Remennik in the math community and Le Dussal in physics, have related this integro-differential Painlevé II equation to the Kadamsev-Page-Vili equation. So from this, there are a lot of connections that you can make between Painlevé equations, integrable models, Kpz, and even random matrix theory. And this is actually the basis that I'd like to discuss during my talk. So as mentioned in the title, there will be three aspects that I would like to discuss with you today. And because freedom determinants are prominent and appear everywhere, I would first like to discuss a few facts about freedom determinants and their relation to integrable systems and what I will then call integro-differential hierarchies. And as an application of these few facts, I'd like to discuss actually two topics. The first is the transition between classical Painlevé II equations to finite temperature Painlevé II equations in form of a Painlevé II hierarchy. And in the third and final part of my talk, if I still have some time, I actually like to talk about some new perspective we could have in the Zakharov Shabat system coming from freedom determinant. Okay, so let's go from Kpz to Fredholm. It turns out that in many problems, a central object that appears all the time is a special type of freedom determinant. So a freedom determinant, which is more or less like the one of the Airy kernel describing the Tracy-Williams distribution. So it's a freedom determinant of an operator that has a kernel of a particular structure, which has a kernel Ks of x and y that can be expressed as an integral of the product of twice the same function with an additive structure. A bit like in the case where you take A to be an array function for the Tracy-Williams distribution, or A being a Gaussian function in the case of the Ginebra ensemble. And it turns out that this kind of kernel and determinant appear everywhere. In the linear statistics of the Ginebra, elliptic, and Gaussian ensembles, in the multi-critical fermions at the edge of interacting systems, in the Zakharov Shabat in the theory of solitons, and also in determinantal point processes. And because this is completely universal, I'd actually like to extend the results that were obtained on an ad hoc basis and see what we can get from this, because this structure is completely universal. So the mathematical setting I'll adopt for the rest of this talk is the following. So I will consider some parameter S, which for Greg was kind of the position of the fermion in his trap. I will consider a smooth function A that has an exponential decay towards plus infinity. So just think of it maybe as a Gaussian function or an Airy function or a Parisi function. And from that function, I will define an operator AS that has a kernel with an additive structure. So AS of x and y will be simply A of x plus y plus s. And from this operator AS, I will construct its square, so the operator KS, which has the same structure as the Airy kernel. And the only assumption I will need is that this operator KS is bounded above by the identity, so that its resolvent is well defined. And the natural objects then to consider with these operators are two types of freedom determinants. So the freedom determinant of infinite temperature, so this, which I will also call this homogeneous freedom determinant, so determinant of identity minus Ks, and a second determinant, which I will call this inhomogeneous or finite temperature freedom determinant, which is the determinant of the identity minus sigma Ks. And sigma here will be a smooth increasing function that go from 0 to any value between 0 and 1, and the asymptotics have to be reached exponentially fast. So just to be clear, you can consider the Fermi factor that Greg was mentioning in his talk, or just the Fermi factor appearing in Kpz. Okay, now that we know what we want to study, let's give a bit more mathematical definitions. So from these operators and from with this equipped with the kernels, I will define a set of variables. So first, let me recall you that I want to study the operators AS and KS, and I will define two extra notations, which are physicist notations, this bra delta and this ket delta, which will project my operators to the value 0. So more or less, if you have an operator which is O with a kernel O of VV prime, then the bra delta O and the ket delta will simply amount to select the element of your operator at 0 and 0. And from this, I will define a set of functions, QP and UP, that are indexed by an integer P as follows. So first, I will consider the resolvent of my operator Ks, which I will multiply by the p derivative of my operator AS, taken simply as the p derivative of my function A. And I will constrain I will constrain this product of operator from the left and from the right to be equal to 0, so that the value are taken to 0. And the function up is more or less the same, but I will add an extra operator at the right of the resultant. And as people are usually more familiar with integral representation of these operators, I actually represented these operators just below in the integral representation. So first, the natural question is, why do I want to define these variables? So firstly, these variables have been defined on an ad hoc basis by many people. Tracy and Widom back in the days, Breza and Hikami in physics, and more recently, Ledoussal, Majumdar, and Cher. But these variables were defined in the literature only for p equal to 0, 1, and 2. And here, I'd actually like to define them for any integer p. And the reason why these variables were defined in the literature is that if you take the Fredholm determinant at 0 temperature, and once again, you take the logarithm and you differentiate it, the first derivative gives you the function u0, and the second derivative gives you minus q0 of s squared. So this actually rings a bell because this is what happens every time with the Painlevé II equation and with Tracy-Widom distribution. So everyone knows this fact, but on an ad hoc basis. And this is much more general and independent of the function a that you choose. And actually, one of the most remarkable fact is that we need this hierarchy because there's a universal law going on there. Actually, there's a universal hierarchy of differential equation governing these variables. If you take the functions up and qp and you try to differentiate them with respect to s, then you'll find this recursion of differential equations. So the derivative of up with respect to s is equal to minus q0 multiplied by qp, and the derivative of qp with respect to s is qp plus 1 minus q0 up. And let me tell you that this is completely universal, independent of the function a. And as I'll try to hint at the end of this talk, this system of equation is actually equivalent to the Zakharov Shabat system, which appears in the lax pair of many, many integrable problems, especially in the AKNS class. And as some kind of teaser of the last part of my talk, for people familiar with the Zakharov Shabat system, for this kind of problems, there is always a scattering approach with reflection coefficient, and the reflection coefficient will be solely the Fourier transform of the function a I chose. And talking about integrable problems, when you have in mind an integrable problems, you also have in mind the fact that you have an infinite amount of conserved quantities in your integrable problems. And that's actually something appearing in this framework as well. There is an infinite set of conservation laws, which are quadratic conserved quantities, and that are expressed as follows. You can write the functions u with odd indices as a function of u's and q's with lower indices. So this is actually nice, and this is as well universal and completely independent of the function a you choose. And both of these results, this hierarchy of differential equation and the conservation laws, were derived for any n by Ledoussal, Majumdar, and Cher in the context of multi-critical fermions. And I tried to extend this for any function a, because they were using a set of functions, the so-called higher order array function, which are a special case of this. And the next natural question is that you have universal conserved quantities and universal equations, but where do you have the physics here? Where do you actually specify which type of function a that you want to choose? You see from this hierarchy of equation that whenever you differentiate qp and up, you always either keep the index p or you increase the index p by 1. So from this set of equations, you'll never be able to actually find a closed differential equation on, let's say, q0 or u0, for instance. So there is actually an ingredient which is completely missing here, is an equation that I will call a closure relation, which allows you to express qn for a certain n as a function of the q's and the u with lower indices. And this is actually where all the physics will be included. And this allows you to obtain actually the Painlevé II equation, and maybe in other contexts, Painlevé 3 or 5 equations if you're in a different framework. And if you remember my interpretation that this set of differential equation is the Zakharov Shabat or a member of a lax pair, the closure relation should actually be the second member of the lax pair of your system. Okay. And I've been asked recently about how you can actually compute numerically this kind of function that appear in the hierarchy, because they look kind of complicated. You have the resolvent of an operator, which you multiply with another operator, and you constrain them with drawing cats from the left and from the right. So actually, there's a natural way to numerically implement this kind of functions using a scheme, the extension of a scheme that was developed by Bornemann for Fredholm determinants. And the idea is actually really, really simple, is because you consider functions on the half positive line R plus, and because they are decaying fast enough towards plus infinity, what you can do simply is first restrict your functions not being on R plus, but on some interval 0m, and then you can compute the integral using some quadrature rule. So basically you would discretize the interval 0m using some points Rj, which you would weight with some weights Wj. And using this kind of rule, for instance, for the kernel Ks, you can just discretize it using this quadrature rule. And you see that if you want to keep this kernel symmetric, then you can also discretize the operator As and locate the points at the same point of your quadrature and actually include the weights of the quadrature. And then the only thing you need to do is actually replace all the operators by symmetric finite size matrices like the one I showed for AS just below. And when you apply actually this scheme, now the resolvent of the operator is simply a finite m by m symmetric matrix. So it takes 5 lines within Mathematica to compute whatever you want. And this is actually useful because you can compute, for instance, the solution to Painlevé II. So I'm giving you now briefly 2 short numerical examples before going to the finite temperature case. So if you take as an example the function a, which is proportional to the area function with a proportionality constant which is between 0 and 1. The function q0, we know that it's supposed to be the solution to Painlevé II, and we know that there's a huge dependence on the coefficient gamma in front. So I plotted for you the 4 functions, q1, u0, and you actually see that there's a huge dependence on the coefficient gamma because it diverges for gamma equal to 1, and it oscillates a lot for gamma slightly less than 1.
Alexandre?
And yes?
There is a question in the chat, which is what's the choice of the weights and the R's by Patrick Ferrari? I guess, are you using the same as in Bornemann or different weights?
Oh, yeah, basically I'm using this Gaussian quadrature. I haven't played much with it, but the Gaussian quadrature is kind of perfect to do it.
Okay.
And the code actually to compute then all of these functions is a small modification from the code of Bornemann. And if any of you want it, I have it in Julia and in Mathematica.
Yes, I also have done it myself. Maybe we can talk after the.
Okay, yeah, definitely. And then a second nice example. Sorry.
Thank you for answering the question.
And the second example is the choice of function a, which is a Gaussian function. So I chose this because this appeared quite recently in a paper from Thomas Bosner and Gino Baek, where they were looking at the real Ginebra ensemble. And from this actually, for this type of function, I still plotted the functions q0, q1, u0, and u1. And there's actually a funny thing going on here. Okay, so you don't have much dependence on the parameter gamma. You don't have oscillations like in the Painlevé case. But when you compute all of the q functions, q0, q1, and then you go even from q2, q3, etc., you see that when you increase the index, you actually have an extra cancellation appearing here. And this actually reminds you of the theory of orthogonal polynomials like Hermite polynomials, where you would increase the cancellation by 1 every time you increase the index of the polynomials. So there might actually something to do here with a general theory of decomposing functions on this set of functions, this q0, q1, etc., etc. And it's a funny thing. Maybe there's something to do around this for numerical analysis. Okay, did I miss something else in the chat? Okay. So, okay, this is what I wanted to say for the zero temperature case. So let's now go to the finite temperature case or the inhomogeneous case before going on to the applications. So now that I studied this generalization for this Fredholm determinant of additive type, and I want to include weight sigma. And once again, think of sigma as being the Fermi factor, for instance. So where do you see this kind of objects appearing? They appear, okay, for the finite time solutions of Kpz, but also for the linear statistics of fermionic point processes, or also some counting statistics for fermions at finite temperature. And this type of objects are solely a generalization of what I told previously, because if you take sigma to be the projector into R+, which is more or less considering the zero temperature case, then you'll find back everything I said before. Okay, so in this setting, I still want to study my favorite kernel, Ks, which is still the product of these two functions with an additive structure. And now, because I have this weight sigma, I don't want to be on R+, but rather on R. So my operators As will now go from L2 of R to L2 of R+, and then I can define an adjoint in this case. And the first thing I want to do to make everything symmetric again is that a bit like in the setting of Grigori, I want to put the weight sigma in between my two functions A. So using the Sylvester's identity, I just commute the adjoint of A to the left, and I now consider the kernel K2, which is completely symmetric. And now that I have this symmetric kernel, I still want to define the extension of the variables I gave you previously, but they're a bit different in this case. In this case, I still multiply the resolvent of my operator K2 by the PF derivative of AS, but I only constrain my ket delta to the right. So I only project to the value 0 to the right. And for UP, I do the same product as before, but I do not put any constraint on the left and on the right. So once again, why do I want to define these variables? I want to define these variables because they were defined first by Amir, Cohen, and Castell in their work in 2010. And as we'll see afterwards, these are the natural variables to introduce. In case of this finite temperature, now QP and UP are the functions, but QP has some kind of vector structure, and UP has a matrix-like structure. And this will be really important for the rest of my talk. And for the people who are more familiar with integral representations, I actually gave in between the integral representations of these variables. So again, why are these variables natural? So once again, the first thing you want to do is take the Fredholm determinant of interest, you take its logarithm, and you differentiate it. If you differentiate once, then in this case, you find the trace of sigma prime multiplied by u0. And if you differentiate twice, then now you find this weighted L2 norm of the function q0. And the natural inner product in this case is the weighted inner product with the derivative of the weights, so sigma prime. And it turns out that the system of differential equation I showed you before can be naturally extended in this case. So once again, for any integer p, if you take the PF derivative of the derivative with respect to S of UP, then you find minus QP Q0 transpose. So in this case, you have a rank 1 operator. And if you take the derivative of QP with respect to S, you find QP plus 1 and the operator products of UP sigma prime Q0. So now the first equation is not a differential equation, but an integral differential equation. And that is actually how you will introduce integral differential equations for this type of problems. Okay. And in the finite temperature case, everything extends quite nicely. You also have an infinite amount of conserved quantities, and you actually have a bit more conserved quantities. Remember that in the zero temperature case, you only had conserved quantities for the functions u with odd indices. Now you have conserved quantities for both odd and even indices. So the one at the top and the one at below. And it turns out that the second equation was actually trivial in the zero temperature case, because if you take sigma prime to be a delta function, then this simply gives you zero equal to 0. So this second equation doesn't really exist in the zero temperature case. So you see here that you have much more structure, both in terms of algebra, because you have vector-like and matrix-like structure, but you even have more conserved quantities. And now that we have this setting, what do we want to do with this? Because, okay, we have this nice generalization of the results that were obtained on an ad hoc basis. We have results for the zero temperature, the finite temperature, we have conserved quantities and all this, but then so what? What do we want to do with this? And the first application I'd like to discuss now is the application of this setting to Painlevé equations, and in particular Painlevé II equations and Painlevé hierarchies. So there will be a number of talks in this conference about Painlevé II, the Painlevé II hierarchy, because it's kind of a universal object that appear in combinatorics and higher energy physics, in gauge theory, and in Riemann-Hilbert problems. So the Painlevé II hierarchy is a sequence or set of nonlinear differential equations that are obtained recursively. And the really first equation is the Painlevé II equation that everyone knows here. And the second equation of the hierarchy is now a fourth differential equation, which already looks a bit more complicated. And then you can iterate, and anytime you increase the index of the hierarchy by 1, you increase by 2 the number of derivative on the functions q. And it was shown quite recently, both in the physics and in the math community, that any equation of that hierarchy can be solved for a particular choice of boundary condition at infinity. And in particular, this was shown by Le Dussal, Majumdar, and Cher. And this was also showed by Kpz, Clays, and Girotti in math. And basically, the statement about the solution is the following. We need to fix the choice of the function a, and we'll choose a function a, which is the so-called higher order Airy function. So you want to solve this differential equation when you differentiate the function a to n times, and this should be equal to x times your function a. And then it was shown that the solution of the nth member of the hierarchy is actually the function q0 I just introduced to you before. So the function q0 with this choice of higher order Airy function. And there has been much interest recently, as said by, in particular, Betea, Boutier, and Valch in combinatorics, and by, okay, a bit longer in history by Perival and Chivitz in higher energy physics. And there's been a few papers recently in gauge theory by Kimura and Zahabi. And all of these results for the Painlevé hierarchy were derived, let's say, for the zero temperature case. But now the natural question is, can we go beyond this? We saw that there's a one-to-one correspondence between the Painlevé II hierarchy and Fredholm determinants. But how about in homogeneous finite temperature determinants? So the question is, can we lift the hierarchy to a finite temperature hierarchy? And for this, there's been in the literature a few perspectives on this. The first one, which I will give to you afterwards, and a second one, which was derived recently by Bosner, Kpz, and Tarikan using Riemann-Hilbert methods. And actually, Sophia will give you a bit of insight tomorrow about this problem on her talk. So yeah, go and listen to her talk tomorrow. In particular, in my framework where I use Fredholm determinants, how do I want to tackle the problem? So I told you that I have this hierarchy of differential equation, the conserved quantities, and I'm missing a precious ingredient, which is my closure relation. And it turns out that for the Painlevé II hierarchy, there's a closure relation that works for any n. So once again, if you take this function a differentiated 2n times, and which is equal to x times a, you define the kernel K2 with any weight that you like that has the right properties, and you have twice of the function a. You get the 2nth member of my finite temperature hierarchy. Then there is a relation allowing you to express q2n as a function of q0, and actually the u's and the q's with the lower indices. And this is an integral differential equation. And you see actually that the structure of the q's is respected, because on the left, think of it as having a vector. Q0 here is a vector. Here you multiply a matrix by a vector, so it's still a vector, and here is the same. So the structure is completely respected here. And using this closure relation, we'll see that we can obtain closed differential equations for the function Q0. And in principle, and actually for the first member, so just for the array function, you can find back like this, the result from Amir, Cohen, and Castell that was derived in 2010. That actually the second derivative of Q0 is equal to S plus T times Q0 plus this term, which is an integro-differential term because you have this weighted inner product here between a Q0 square and sigma prime. And you see once again here in this equation that the structure of Q is completely preserved, because on the left, Q0 is a vector, Q0 here is a vector, Q0 here again is a vector, and this inner product or this norm is only a scalar. So you see that you have much more structure in this differential equation. And as I said in my introduction, if you take sigma to be the projector into R plus, so the zero temperature case, this of course reduces back to the standard Painlevé II equation. So this is more or less actually how Amir, Cohen, and Castell derived their equation in 2010. So now let's try to go beyond this. Let's try to get the second member. So for the second member of the hierarchy, now you get the function A, which is the second member of this higher order array function that solves the differential equation of A differentiated 4 times is equal to X times A. Once again, you take the same kernel that we've been studying for half an hour. You take the first function of my hierarchy, and this function here solves another integral differential equation, which is a generalization of the second member of the Painlevé II hierarchy. And as you can see, this equation is a bit involved, but once again, it respects the structure of the vector structure of Q0. And if you want to go beyond this and have actually the third, fourth, or fifth member of the hierarchy, then you have to listen to the talk of Sophia tomorrow. But the equations become more and more and more involved, and actually then you can't even put them into a single slide. So that's the first application of my framework. And for the second application, as I don't have a lot of time remaining, I'd actually like to talk about the Zakharov Shabat system, as I know that most of you are familiar with this. And actually, I think that even half of you actually wrote that of the paper. So the Zakharov Shabat system is a differential equation that arises as a member of a Lax pair of many integrable problems arising in the AKNS class, including the KDV, MKDV, NLS, KP, so it appears a bit everywhere. And the setting is the following. The setting is that you consider a 2x2 matrix, X, that depends on 2 parameters, Z and S. So think of Z as a Fourier parameter and S as a space parameter. So it's the same S as the beginning of my talk or the S of the lecture of Gregory. And let's consider a certain function A as before, and we want to consider the first function of my hierarchy Q0. And then finally, you define the Pauli matrix sigma free, and finally this differential equation on X. So this differential equation is an equation for 2x2 matrices, and it appears everywhere as a member of a Lax pair of many problems. And it turns out that for this differential equation, you can actually ask that when you take your Fourier parameter to go to plus infinity, you can ask that the matrix has a Laurent series. And the really nice thing is that you can actually express the Laurent coefficients of this matrix with the hierarchy of variables I just showed you in my presentation. In practice, the P+1 coefficient of the expansion is actually composed of the functions QP and UP. And this is actually surprising, but I told you before that the infinite hierarchy of differential equation was equivalent to the Zakharov Shabat system. And actually, this is the reason why. And these variables QP and UP, I just reminded you their expression below. And that's actually quite a nice interpretation because it gives you a fresh look on the Zakharov Shabat system and the further connection between Fredholm determinant and the Zakharov Shabat system, which appears a bit everywhere. And even more, the other fresh look or the nice property you have is the following. So I know that most of you are familiar with Riemann-Hilbert problems, and we know that we can re-express the differential equation of the Zakharov Shabat system in terms of a Riemann-Hilbert scattering problem, where you would actually find a solution X which has nice properties in the complex plane. And in particular, you would impose that the matrix X has a jump along the real line, and the jump matrix is actually expressed in terms of some reflection coefficient that arises from a scattering problem. And in my framework, you can show that there is a nice connection between the function A that you chose originally, like for instance, the Gaussian function or the Airy function, and the reflection coefficient. So the relation between the two is a simple Fourier transform. So it's really, really, really simple. And it's actually nice because this hints that you can actually solve quite universally the Zakharov Shabat system in terms of Fredholm determinants. And if you want to go beyond that, I considered the Zakharov Shabat system just previously with a special function in my differential equation, which was this Q0. That was the first member of my hierarchy. But it turns out that for many, many applications, you don't have such structure. You just have a function Q inside that has no particular structure. Maybe you have a Gaussian function, an Airy function, or even a delta function. But you don't usually have a function that can be expressed as the second derivative of Fredholm determinant. So for this type of problem, you have a natural question in this framework actually, is that if you consider any function Q, can we construct a function A, and can we construct it in a unique way so that Q can be written as the first member of my hierarchy, meaning that Q of S can be expressed as an operator AS multiplied by the resultant KS and constrained by these K variables. For people used to studying scattering problems and that realize that A is solely the Fourier transform of the reflection coefficient, you'll realize that actually the mapping from Q to A is nothing more than a direct scattering transform. And sometimes this is actually called the nonlinear Fourier transform in electrical engineering. And the mapping now from A to Q is actually called the inverse scattering transform. And you see that the inverse scattering transform in this framework is actually explicit, if not trivial, because the expression is written just here. Some research to do about getting exact solutions to integrable problems using Fredholm determinants. And I think that for KDV and KP, this was hinted by Popper in a few papers, where he actually showed that the solution of KDV and KP was related to Fredholm determinants. But this is actually much more general, and this arises from the fact that for a lot of models, a member of the Lax pair is actually the Zakharov Shabat system, and the Zakharov Shabat system can be solved by Fredholm determinants. So as a kind of a conclusion or outlook of what I wanted to say to you today, I wanted to emphasize that Fredholm determinants are at the interface of many problems. In their interface of random matrix theory, nonlinear differential equations, AKNS, Painlevé, even Kpz, and they're also related to nonlinear Fourier transform. So there should be something that is hidden behind this, something much bigger. And this is actually something I'd like to dig in my further research in the coming months or years. And if I could give you a bit, some outlooks that we could study from this, there are a few things that come in mind to me. The first is that we saw that there was an extension of the hierarchy of differential equation from 0 temperature to finite temperatures for the Fredholm determinants. So there should actually be a finite temperature extension of the Zakharov Shabat system, meaning that there should also be a finite temperature extension of the AKNS class. And that would be kind of interesting to study. The second object we could also study is a Fredholm determinant that now has two different measures in it. Let's say a measure sigma like before and another measure mu. And in which case could this appear? It could actually appear if you want to study linear statistics of fermions at finite temperature. So one of the two measures would actually encode the temperature, and the other measure would actually encode the linear statistics you're interested in. And finally, maybe there's something to do about general explicit and numerical solution of the inverse scattering transform of the Zakharov Shabat system using Fredholm determinant with application to KDV, NLS, and many, many, many more problems. And on this, I'd actually like to thank you very much for listening, and I'd be happy to discuss with all of you.